Last week, you worked with a site by species data matrix for Bryce Canyon National Park. In this lesson, we will analyze the site by environmental data frame for the same plots from the file brycesite.r. Last week, the bryceveg.r file was a data matrix because it was composed of a single variable type. It was numerical. Today, you're going to be working with a data frame that consists of multiple data types, both numerical and text. You may have a single humongous data frame that includes both your site, your species, and your environmental variables. And there are times when that can be the most expeditious thing to do. But a lot of times in R, because there are different properties between data matrices and data frames, you'll want to parse them out and treat them separately. And so that's why last week we had one type, and this week we have another type. And in many of the upcoming weeks, you will also have these two types of data sets parsed out, site by species and site by environment. So for today, go ahead and open RStudio, set your working directory, and then library the packages that are listed for today. Then you're going to read in the brycesite.r data with this function, creating an R object that I call site. And there's a bit in this that is new to us. It's this strings as factor equals true. Recall that data frames can have a mixture of numerical values and categorical text values. Categorical variables are called strings. And so this phrase, strings as factors, makes R treat the text categories as quantitative entities and not just words. You need to do this for analyses. Okay, so now that the data frame is in R, there's another bit of code that we haven't used before that is very useful, and that is attach. This is a command that is very useful for data frames in R because it means that you don't have to specify the R object and the column name every single time you want to use it. You just tell it the column name. In the online notes, I give you example of code with and without using the attach function, and you can see that it is much more streamlined when you use attach. This is for data frames. Okay, so now take a look at the data. And you can see here that you've got numbers and words. I have a key in the online notes about what each of the column names mean. When you have your own data, make sure that your column names don't include spaces, that they don't have any symbols in them, or they don't have long names. You're going to want to use abbreviations, but make sure that you have a legend and metadata somewhere. Not just for others, but also for yourself so that you can remember, what did I mean here again? Okay, so some of these variables are likely correlated with each other. So the first thing we're going to do is we're going to plot the joint distributions of some of these variables in order to be able to quickly see whether or not there are any possible relationships. And then we can do some formal correlation analyses in order to be able to determine the strength of any such relationships that we might detect. One of the things I emphasize is the importance of plotting your data because it's so easy for us to be able to quickly see any patterns that may be present. So recall from last time that the plot function in R specifies the x-axis first and then the y-axis. And so in this case, I wanted to see whether or not there was a relationship between elevation as a function of aspect. And so that's what this command says. And when you plot it, because both elevation and aspect are numerical, then the result is called a scatter plot. Check it out. There's no trend in the data. There's no pattern. It looks like a shotgun blast, and that, in fact, is the technical term for such a relationship in a scatter plot. This means that these variables are likely not correlated with each other, And that makes sense because there's no ecological reason to believe that elevation and aspect would be related to each other. If you wanted to verify that, you can do a formal correlation analysis in R using the COR command. This gives a Pearson correlation. And when you do this, it returns a value, in this case, of 0.09244 blah, blah, blah. That's the Pearson correlation coefficient, little r. That's a number that ranges between -1 and 1 and indicates the strength and the direction of a relationship between two variables. In this case, because it is so close to 0, that indicates that there is no relationship between these two variables, which corroborates our graph. The Pearson correlation is R's default. This is the parametric version. It assumes a linear relationship between continuous variables. A Spearmint correlation is the non-parametric equivalent. It uses ranks and so can also be used for ordinal variables. It makes no linear assumptions. And so because it relaxes these assumptions, the trade-off is it's less powerful statistically. But if you do get a significant value with it, it's more conservative. If you want to do a Spearmint correlation in R, you have to tell R that the method you want is Spearmint. And in this case, it returns a value, once again, that's close to 0. Again, corroborating that there is no relationship, significant relationship between these two variables. You can also plot variables that are not numerical. For example, this line of code plots a numerical value, which is aspect in degrees, against a categorical one, soil depth. And when you do this, the result is a box plot rather than a scatter plot. The overlap of these boxes indicates that there is likely no statistical correlation between these two variables. And again, I had no ecological reason to think that there would be. I'm just choosing these as examples. You can try to do a correlation analysis on these variables, but R gives you an error message because correlations can only be computed between two continuous numerical variables. And if you plot two categorical variables, then you get this. This type of graph is much more complicated to interpret. So anyway, play around with plotting different variables. There are times when you may want to examine 3 variables at once, like the interrelationship among elevation, aspect, and soil depth. And in order to do that, having plots side by side can sometimes make patterns in the data more clear. So to do that, you first have to tell R, hey, I want you to put multiple graphs on the same page. And that is this line of code up here. This first bit of code, mfcall, sets up graphs side by side. If you wanted graphs stacked one on top of another, then it would be mfrow. And this C12 specifies 1 row, 2 columns here. So now that we've told R this is the format of how we want things, then we tell it what we want to plot. And these 2 lines here are for the 2 graphs that we're going to have side by side. The plot lines include elevation as the x-axis, it's mentioned first, and aspect value as the y-axis here mentioned second. And each is plotted for only a certain soil depth. This double equal sign indicates exactly equal to deep. And then down here, the exclamation point equal sign means not equal to. So this first line of code is for deep soils, and then the second line is for the shallow soils. So because both elevation and aspect are numerical values, then you get 2 scatter plots with the deep soils on the left and the shallow soils on the right. And once again, you can see that there really are some, there's lack of pattern in these data over here. Maybe there's something going on at this particular band of elevation here. That could be interesting. and so forth. So you can play around with stacking these variables one on top of another rather than putting them side by side, and you can see how easy or difficult it is to interpret them. Because we read left to right rather than from top down, having graphs side by side is often considered to be easier to understand. You have to remember to tell R to go back to one graph when you're done with this by telling it you want C of 1, 1. If you're interested in at least one categorical variable, then box plots can quickly give you lots of information. So here's one from the function of box plot, elevation as a function of depth. And then here's a little key about what each element of the box plot means. So first off, these strong lines in the middle here are the median values. And then the shaded boxes represent the range of values that are between the 25th percentile and the 75th percentile. That's the interquartile range. The whiskers indicate the quote-unquote maximum and minimum values of your data, but they're not technically the true maximum and minimum values because there are other data points you can see up here and down here. The maximum and minimum you can see here have a formal statistical definition here, and that values beyond that, these little circles that are designated in the box plots, those are extreme values relative to the rest of your data, and those are outliers here. So in this case, you can see that the median values differ, but there's a lot of overlap in soil depth with elevation here. So that indicates that we really ought to do a formal statistical test to see whether or not there is a significant difference between them. And so a t-test can do that, for example. And in this case, I've set the assumption var.equals false means that we do not assume that the variance in the data is the same between these different soil depths here. And so when you run this t-test of these mean values, then this is what you get here. And the significant p-value here indicates that deep soils do not occur at the same mean elevation as do shallow soils. And ecologically, that makes sense. The non-parametric equivalent of a t-test is called a Mann-Whitney U-test or a Wilcoxon-Rank sum test. Non-parametric tests relax a lot of the data assumptions, but to do so they sacrifice statistical power. So in this case, if you wanted to do a Wilcoxon-Rank sum test on these data, the command is this, and then the results are here. This continuity correction down here is an automatic adjustment that's made to approximate a binomial distribution, since we have a binomial type of variable, deep and not deep soils here. Now I want to stress that I am presenting both for the correlation analysis and for this t-test, the parametric and the non-parametric equivalents, simply for educational purposes. You should not try both out and see which gives you the better p-value or more significance. That kind of data fishing is a big no-no. Don't do that. So this is simply for educational purposes. You should have an a priori reason for choosing a given test. For your assignment, you'll be using multiple data sets. You'll start with the ground beetle data frame from last week. And one of the variables included in this data frame is called habitat. There are 3 types of habitat in this data set where beetles were collected, and these are edge or ecotone, grass indicating grassland or meadows, and wood indicating woodlands. You'll work with this data set to find out which of these three habitat types had the most beetles in terms of species richness and in terms of numbers of individuals, abundance. And in so doing, you'll also learn how to cope with cells with missing data. Prior to now, you've worked with single data sets, a site by species data set last week and a site by environment data set today. Now you'll work with both simultaneously to determine whether plant species richness varies by habitat type, using the skills you've gained today in making and interpreting box plots and t-tests. You'll be using the grassland.community CSV file, which is a site by species data matrix, and a plot.metadata CSV file that is a site by environment data frame. We'll be doing something similar, working with multiple data sets in upcoming weeks. So this lesson concludes the introductory materials for this class. Next week, we will finally be getting into the heart of working with ecological community data.